In this video, we are going to explore the so-called Fischer Esterification reaction, which takes a carboxylic acid starting material, and what is going to happen during this reaction is the carboxylic acid starting material that I'm circling here reacts with an alcohol in the presence of an acid catalyst, and the reaction will result in replacement of the hydroxy group with the O-alkyl group from the alcohol, thus resulting from that substitution reaction in the formation of an ester, a molecule that has a carbonyl group directly bonded to an O-alkyl group, as we see here on the product side of this reaction. This will follow the general theme that we have been seeing and developing for nucleophilic acyl substitution reactions, where we'll have a nucleophile come in at some point during the mechanism, attack the carbonyl carbon. Ultimately, a leaving group will leave, therefore ultimately resulting in replacement of the hydroxy group with the O-alkyl group from the alcohol. In this video, we're going to go through the mechanism for this reaction and explore some of the details of predicting products of these types of reactions. So one thing that you will notice as we begin to look at this reaction in a bit more detail is that I have this shown as an equilibrium arrow. And indeed, this is an equilibrium reaction. And in order to force the equilibrium to favor the side of the ester product, we can apply Le Chatelier's principle from general chemistry in order to devise ways to go about forcing the equilibrium toward the side of the products. Some of those ways that are used to force the equilibrium toward the side of the product is to use an excess of one of the two reactants here. Generally, the excess is used of the alcohol reactant, forcing the equilibrium toward the side of the product. Another way that can be used to force the reaction toward the side of the product is to do something like distillation to remove product as it forms. So by distilling, if we heat up the reaction mixture to the point that the lower boiling point product, which perhaps is the ester, depending on how long these alkyl chains are, if we can remove that from the mixture by distillation as it forms, that will also, via Le Chatelier's principle, perturb the system and force the equilibrium toward the side of the product to maximize the yield of the ester product in this reversible reaction. So let's go ahead and take a closer look at this reaction to understand the mechanism of how the reaction is taking place. To explore the reaction mechanism, what I'm going to start with is butanoic acid reacted with ethanol. So let's go ahead and look at that mechanism. And our mechanism that we're listing out here would be the same for whatever carboxylic acid reactant we want to use. I'm just going to use butanoic acid in this particular example, reacting with ethanol in the presence of acid catalyst, which could be sulfuric acid catalyst or whatever other acid we wish to use there. And as we go through this mechanism, we're also going to use this as a way of illustrating how we go about solving the mystery of how mechanisms work. So in this reaction, experimentally, we could carry out this reaction and we would know that the reaction yields the ester that I have shown here on the product side, because we could isolate that ester and we could use techniques such as NMR to enable us to identify that ester product. Likewise, we could also detect the formation of water in the reaction mixture, so we'd be able to evaluate relatively easily what the products of the reaction are. But understanding how to go from the reactant to the product, in other words, how to determine what the mechanism is for this reaction experimentally, poses some additional challenges. One common way that is used to determine experimentally mechanisms, to provide evidence for a particular mechanism, is using isotope-labeled precursors, where one or more specific atoms of the starting materials carry a unique isotopic label that can be determined in the final product. So in the final product, we can look at what the location of that isotopic label is in order to better understand how the mechanism is taking place. So in the case of this reaction, one question that might arise is we might be wondering, okay, when we envision that in our final product, we have this O alkyl group that I've circled in gray. The O alkyl group could include the oxygen atom from here plus the alkyl group from ethanol. It could include the oxygen from here, that is the carbonyl oxygen, plus the 2-carbon chain from our alcohol, or that oxygen in the final product could be derived from the oxygen atom of ethanol. So to determine which of those 3 oxygen atoms from the starting material ends up at this position of the product or elsewhere in one of the other products, such as the water product or the carbonyl there, what we can do is we can run a reaction where we have a strategic isotopically labeled precursor. So our precursor, in other words, our starting material. So for example, oxygen 18 is a common isotopic label. That is oxygen which has an extra neutrons so that it will have a molecular mass of 18. So as we write out this reaction mechanism, we are going to consider that this oxygen from ethanol is not the standard oxygen 16 isotope, but instead it's oxygen 18 with a couple of extra neutrons. That oxygen is going to behave the same in the mechanism as it would if it was oxygen 16, but it will have this label that allows us to track exactly which oxygen atom in our final product mixture carries that particular label to give us clues about how the mechanism actually took place. So let's go ahead and walk through this. So walking through the mechanism, what we would see if we evaluated our final product here is that the oxygen 18 label ends up specifically at this location of our ester product. The other oxygen atoms, here and here in our starting material, here and here in our product, carry the oxygen 16, the standard normal old isotope. So how do we go about doing this? We need to make a mechanism that will explain what we observe experimentally, that the oxygen 18 label ends up here in our product. So we need to make sure that our mechanism can account for that observation. So let's go ahead and write out a mechanism that will account for that observation. So we're going to start with our carboxylic acid starting material, and we will react with our acid first. Acid is the catalyst in this reaction, and so what's going to happen is the first step will be protonation, as is typical when we have a reaction where there is acid present. So what do we protonate? Well, we've seen time and time again, when there's a carbonyl present, the carbonyl is very subject to getting protonated because the product of this protonation reaction is stabilized by delocalization of electrons by resonance. So we'll go ahead and sketch this out here, that we will have a new bond between that oxygen and our proton here, positive formal charge on the oxygen. Now, we could draw a second resonance structure here if we wanted, where we would be able to move the pi bond up onto the oxygen, put the positive charge here on the carbon, and an actual additional resonance structure, we could take the lone pair from the oxygen, move those over to make a pi bond here to share that positive charge across both of the oxygen atoms here. That will help make this step relatively favorable, is the fact that the resonance can delocalize that positive charge over multiple atoms. This step also results in this carbonyl carbon becoming more electrophilic than it was initially. So the protonation step there serves to create a stronger electrophilic carbonyl carbon. And that's why I've put that as delta plus plus to indicate that this carbon over here, now that we've protonated, is extra positively polarized. Now, with that positive polarization in mind, what's going to happen now is that a nucleophile will come in and attack that carbonyl carbon. And the nucleophile that we have available here in our reactant is going to be our alcohol. So the nucleophilic alcohol attacks the carbonyl group that is electrophilic. So we'll show that happening with our alcohol coming in, and I'm going to go ahead and remember to label that is oxygen 18 to emphasize where the isotopic label will end up. Oxygen lone pair comes over, attacks here at the carbonyl carbon. That forces the electrons from that pi bond up onto the oxygen, and we'll go ahead and draw out the product that results from that step. Like so, lone pairs on our oxygen there, lone pairs on our hydroxy group here as well. And then our new covalent bond goes in black here over to the oxygen, like so, and a 2-carbon chain. And there will be one set of lone pair electrons there, and our hydrogen bonded there as well. And that's going to result in a positive formal charge being present on the oxygen atom, like so. And so now at this point, what happens in this mechanism, moving us onward toward our product, is that the proton that is present here, conferring that resulting in that positive formal charge on the oxygen, that proton is going to be lost. And so our third step of the mechanism we would describe as a deprotonation step. So step 3, deprotonate. And we can show that happening by bringing in some source of base. Our base here that we have available from the reactant side of the equation, we just need a weak base here, and the alcohol will do the job of that. And so alcohol comes in, grabs a proton from our reactant there, forcing the oxygen-hydrogen bond to break, and that is going to give us then, on the product side of this equation, we'll have protonated our alcohol, like so, and then our other product of this step will be this intermediate, where we have a carbon that is directly bonded to 2 hydroxy groups, boom, boom, and directly as well bonded to that O-alkyl group. So O-alkyl with our 2-carbon chain there, keeping our label in place there for our oxygen. This would be our oxygen 18. And now, at this point, we have created this intermediate. And after we have created this intermediate, what's going to happen now is that one of the 2 hydroxy groups picks up a proton. So in this series of 2 steps here, what we are essentially doing is we're deprotonating and then we're reprotonating. So the net effect is that we are moving the proton through steps 3 and 4 here from being attached to the O-alkyl group oxygen to becoming bonded to one of the 2 hydroxy groups. And it doesn't matter which of these 2 you select in this protonation. So we're going to bring the proton in here. And I'm going to abbreviate the proton just as H+. You could also have grabbed a proton from here instead, where I'm highlighting with my laser pointer. That could act certainly as an acid as well. But in the interest of simplicity, I'm just going to show the protonation occurring here on our generic acid. So lone pair comes over, grabs a proton from the acid, and that's going to result in the formation of the product that I am drawing out now, where we still have one of the 2 hydroxy groups is not protonated, the other one now is protonated, so it's H2O here with a positive formal charge on the oxygen. And then we also have our O-alkyl group, where the oxygen 18 label still resides. I'm going to put an 18 there to designate that. Now, coming onward, moving along toward the product, what's going to happen now is that water, which we have created here within our organic molecule, is a very good leaving group. And so what will happen is that the water will break away. And as the water breaks away, we can also, in order to maintain an octet on this carbon atom that I'm circling, we can simultaneously move a lone pair of electrons down from the oxygen here to create a carbon-oxygen double bond. So we'll go ahead and do that, drawing out my product of this reaction step. We'll have our carbon-oxygen double bond there. That oxygen now will have a lone pair of electrons and the proton still attached there because we had OH group here. We moved the lone pair down to make a pi bond, down to make a pi bond. So we'll get a positive formal charge going there on it. And then additionally, we have our O alkyl group here. So I'll plug in my O alkyl group, and it still has that oxygen 18 label on it. So I plug in the oxygen 18 there. The other product of this step would be the water leaving group, which has left. And now at this point, we are almost to our final observed product, where the final observed product, we just need to go from here, where I'm just circling, up to here. And in order to do so, all that we need to do is a deprotonation step, because our intermediate here, I'm circling, has the positive formal charge. We need to get rid of that positive formal charge. We can do so by deprotonating. And so the last step of this mechanism, which will be step 6, is a deprotonation step. I did not label step 5 here. I have the arrow, but I don't have it numbered. So step 5 was the leaving group water leaves from the molecule, creating this as our most stable resonance structure resulting from that reaction. And then finally, we deprotonate, and I'll show the deprotonation here by taking a lone pair electron, set of lone pair electrons from the water. You could also use methanol here as the base, it doesn't matter which. Grabs the proton from the acid, that forces the hydrogen-oxygen bond to break and the electrons to go onto the oxygen to give us, as the finale of that, our final product, where we have our carbonyl group is what we just formed by deprotonating that group that I'm highlighting here on the bottom right corner. And there's also that oxygen 18 attached to the 2-carbon O alkyl group. And so the mechanism that we've written out here, in other words, supports and provides a rationale for how we ended up with the oxygen 18 label in this particular position at the upper right-hand part of the screen, where we are seeing that label in actuality when we use analytical techniques to evaluate where the oxygen that has that isotope label ended up. We can trace that and we can justify how that oxygen ended up there based on the mechanism that we have sketched out here of our series of proton transfers and nucleophilic attack. So that is going to be our route for getting to the final product here. And we could run similar experiments with other types of labels, like labeling carbons with carbon-13 rather than carbon-12, and so on, to help us piece together a logical mechanism for whatever type of reaction we were looking at. Isotope tools have been very, very instrumental in helping us provide evidence in support of mechanisms that we hypothesize for reactions, such as is the case for this one. Now, to solidify our understanding of the Fischer esterification reaction, we're going to do one additional example problem where we're asked to predict the major organic product of this reaction. Now, this may initially throw you off because as you look at the reactant, you only see one organic reactant here. But that one organic reactant has both of the functional groups you need to do a Fischer esterification. And so as a result, what can happen here is an intramolecular reaction where the alcohol group from this molecule reacts with the carboxylic acid group within that same molecule. So I'm not going to go through the complete mechanism for this reaction, but we'll do the first couple of steps to make sure we are on our way to the correct product. So with the acid catalyst, what happens in the first step of these mechanisms, as we saw in our last example, is that we get protonation. So the carbonyl group comes over, grabs a proton from the acid, and that's going to result in the formation of this intermediate, which I am drawing out now. So we bring out in the proton onto this carbonyl group of our carboxylic acid, like so. And then at that point, this carbonyl carbon that I'm labeling in green is super positively polarized. And as a result, the alcohol group that's present within that same molecule with its lone pair electrons in blue are going to come around and attack intramolecularly that carbonyl carbon. And so what happens here is first, protonation, always the first step when we have a strong acid present as a catalyst. Second step is that the nucleophilic alcohol group attacks the electrophilic protonated carbonyl group. And this is an intramolecular attack or an intramolecular reaction because of the fact that we have both functional groups that we need to react within the same structure. And this intramolecular reaction, due to the fact that we have a chain of carbons here that I'm highlighting in red on my reactant side, and that chain is going to be linked a second place here between the oxygen and the carbonyl. That's going to form a ring because once we make this covalent bond that we're showing in blue, we're going to have a continuum of atoms here. And so what we would need to do here in this continuum of atoms is we need to figure out how many atoms would be in the ring. And the way that we can do that is we can number, and this doesn't have to follow IUPAC nomenclature numbering or anything like that. We're just trying to piece together who's bonded to whom in our final product. So to sort that out, I'm going to number the carbonyl carbon 1, 2, 3, 4, 5, and I'm even going to number the oxygen atom here just so that we can keep track of who's who in drawing out the product. So what we should draw here then is we need a 6-atom ring because we have atom number 6 here, the oxygen, coming around and bonding to carbon number 1. So therefore, that's going to make a 6-membered ring with one of the 6 atoms of that ring being an oxygen. So I'm going to plug the oxygen in here, and then I'm going to draw the other 5 atoms, the carbon atoms, like so. And then what I'm going to do is go ahead and number these. We said the oxygen was number 6 in our original structure, so it's still number 6 in the product. And that number 6, our oxygen, is connected to 5, 4, 3, 2, 1. So therefore, I'm going to go around the ring and go 5, 4, 3, 2, 1. No, it doesn't matter whether you go around the ring clockwise or counterclockwise. You're going to get the same product one way or the other. And then what I have to ask is at each of those positions that we have numbered, what else is bonded there? So at position 6, which we have labeled over here as 6, there's not just an oxygen atom there. There's also a hydrogen bonded there and the connection to carbon 5 and the connection to carbon 1, the connection that we just made to carbon 1. So at position 6, our oxygen should be connected to carbon number 5. It should also be connected to carbon number 1 because we made that new covalent bond, and it is. There's also a hydrogen there, so don't forget to put in that proton. So I'm going to plug in that proton like so. Lone pair electrons, there's still one set there. And so as a consequence of that, that oxygen is going to have a +1 formal charge. That is all that's bonded at position 6. We come to position 5. All that's bonded at position 5 are the implied hydrogens, an oxygen, and a carbon. When we look at position 5 in our product, we have oxygen, carbon. Perfect. Same thing at position 4. When we look at position 4, we ask what's bonded there. It's directly bonded to carbon 3 and carbon 5. That is it. Position 4 over here, directly bonded to carbon 3 and carbon 5, and that is it. Going to carbon number 3, we look over here. It's directly bonded to carbon 2 and carbon 4. Number 3 here is directly bonded to carbon 2 and carbon 4. So on and so forth. We get to position 1, and we have a little more work to do here. At position 1, which I'm highlighting, position 1 is connected to oxygen number 6. We already have that bond in there. Number 1 is also connected to 2 hydroxy groups, the hydroxy group here and the hydroxy group here. So we need to plug in 2 hydroxy groups directly connected at carbon 1. So 2 hydroxy groups, OH and OH. And from here, I am not going to go through the rest of the mechanism for this reaction. The steps are completely analogous to what they were for the last mechanism. You should be able to sketch those out on your own and be comfortable with doing so on a quiz or something like that. But ultimately what's going to happen is that through a series of proton transfers, in other words, protonation and deprotonation steps, ultimately one of these 2 hydroxy groups is going to leave as water because it will become protonated and then break away. The other hydroxy group is going to become a carbonyl, and ultimately this proton in blue at oxygen number 6 leaves as well to give us an ester in our final product. And that's why the reaction of the alcohol and carboxylic acid is called Fischer esterification, is because the final product had better be an ester. So this is definitely an ester. It happens to be a cyclic ester because we have this ester group where the carbonyl and the single bond to oxygen there, the single bond to oxygen is part of a ring. So this is a cyclic ester, but it is definitely still an ester that we have made as our final product. There is a special name that we use to assign, or a special functional group name that we use to assign to a cyclic ester. A cyclic ester takes the special functional group name of lactone. So the term lactone would be the most accurate, most descriptive functional group to describe what we have created here. So a synopsis of when a lactone will be formed is that if you have an intramolecular Fischer esterification, intramolecular Fischer esterifications are going to yield lactone products because they are going to make an ester that is cyclic via the intramolecular reaction of an alcohol group with a carboxylic acid in the same molecule to form a ring which contains an ester functional group. Lactone groups are interesting and useful because they are very commonly found within drug molecules. In fact, a variety of antibiotics have this type of ester that is part of a ring. And in many of those cases, the ring is actually quite large, meaning 12 to 16 or more atoms in that ring. And in those cases, those types of groups are sometimes referred to as macrolides, for macro means large, and the lide part is referring to the fact that it has a lactone present in it. But the lactone is just our general term, our general functional group term to describe a cyclic ester.